So if you think of von Neumann computing as a left brain, symbolic, structured, if-then-else, binary sort of a computing, then synapse or neuromorphic computing, brain-inspired computing, is about pattern recognition, slow, synthetic, parallel. On one hand, you have flops, floating point operations per second. On our side, we have SOPs, synaptic operations per second. To give you a perspective of, since the project started where we are, project actually started in 2004 with a single person, leading from then on to an Almaden Institute on Cognitive Computing, which actually, Christoph, you were present at. And so it's really great to have you. And then from then on, we worked on the largest Blue Gene L, the largest Blue Gene P, and largest Blue Gene Q to carry out increasingly larger simulations. This is, of course, Henry Markham's favorite one. And then we won the DARPA Synapse project grant and worked very closely with Todd Hilton, Gil Pratt, and Dan Hammerstorm. We mapped out the wiring diagram by collecting the largest data set. We created the worm-scale chips with 256 neurons. I mentioned the simulation at the scale of human brain with 100 trillion synapses to development of the True North ecosystem. So not only do we have a chip, but we have an end-to-end programming paradigm from user interface, deep learning, down to a programming language, firmware, as well as the whole user flow and debugging tools, right? And on top of that, we have created various boards, and we are making plans by December of next year to create a 128 chip system that should happen. So we are now just at the beginning of the next generation. In the next generation, we already can imagine new chips, new software, ecosystem, new training, new systems, and even new sensors, and new algorithms and applications, which will fundamentally allow us to create completely new neural networks. And we have a roadmap for building systems by using example of the scalability of True North. And the whole idea is a sort of a spiral. We went from architecture to simulation to chips to applications. And now that we have the benefit of insights, not just from our work, from work from colleagues as well, that we can actually, again, do another turn on the spiral. And the ultimate vision, which I believe will be possible before 2020 ends, is that we will be able to produce a brain in a box, which was the original vision of Synapse project, 10 billion neurons in 2 liter, 1 kilowatt. This is no longer science fiction. It is happening. So the project has received a lot of adulation. I just want to flash it in front of you real quick. But this is very important. Last fall, we had a chance to present the tiled board to President Obama, and we received a real signed letter congratulating the team, which has become a prized possession for our team. And it was presented to the House panel on science, as well as Senate panel on science. And with that, I would like to thank the DARPA program managers for their vision, their partnership. I'd like to thank our current customers, Air Force Research Lab, DARPA, Lawrence Livermore National Lab, Army, and hopefully Navy coming soon. This is for the collaborative work. I saw Professor Philip Wong, who has been part of the project since very early on, Department of Energy, 8 IBM labs and fabs, and just the Synapse project itself at 6 universities, but of course now we have expanded. I would like to thank Livermore and NNSA for all the supercomputers that they gave us, and all my wonderful colleagues. It's really a joint work, and some of them at Almaden today. With that, thank you very much for your attention, and thank you for inviting me, Murad. And please remember to see my colleague, Dr. Paul Marola, today evening for the demos. John, so it's the question we agreed upon, right?
Pardon?
The question we agreed upon, right?
Exactly. No. So some of us do backpropagation and spiking neural networks and some other things. But the question that I have is, Right now, your training is done offline.
Yes.
And I think it would be fantastic to implement all that on a 28-board chip. Do you have any plans to put that learning algorithm into the chip and accelerate that portion of it?
We certainly do.
Yeah.
And it's again, the accelerating learning has to be done with far more care than accelerating inference, as you can understand, because you don't want to tie yourself down so that you cannot explore the full space of learning algorithms. But I'm certainly happy to talk to you about this.
So
Karl-Heinz.
for your brain in the box, 1 liter, you would definitely
Two.
need 2 liters. Sorry, you would
Karl-Heinz, this is not fair.
I give you 10 liters.
Okay.
Okay, but you would still need a different solid-state circuit technology. So what will be your choice?
7 nanometers
That would be sufficient to put a brain in a box
will
of
be
10
sufficient.
liters. I see.
But just to be very fair, IBM has a huge investment in advanced process technology, right? And we are continuing to do that. And as such technology becomes available that can be integrated with the existing process, we stand ready to take advantage of it. So I'm an engineer. I'm not a scientist, and I want to make things work. So I'll accept anything that works. Thanks, Karl-Heinz.